welcome to the Data Science Decoded podcast. Now we are quite on track, at least trying to be. And I am here with Mike and Nir. How are you guys?
Howdy, doing good.
Doing well. I think it is the earliest podcast we are recording because it is morning in Israel, 8:40, and I have some troubles to getting up early throughout all my life. So hopefully, my brain will be in good condition throughout this podcast. So, but if I'm talking bullshit, please stop me.
Yeah, it shows how dedicated you are, Mike.
Yeah.
Sacrificing sleep in order to record an episode. But cool. So without further ado, let's look at the paper today. So to our listeners, the title is an exploratory technique for investigating large quantities of categorical data. So in a sense, it will be about trees and decision trees. And our listeners, the dedicated ones, can remember we already did one episode. I forgot the name of the paper, but it was from 1960 something. Well, they talk about it here. It's called the CHAID, Automatic Interaction Detection. And this is like a development of that paper. So this was published in 1979 by Gordon Vivian Kass. He's from South Africa. And I tried to look up some information about Gordon prior, and I couldn't find a lot, except, and Nir is going to like it. Well, I don't know if it's so positive, but he passed away last year. So you can, there was some posting about that, and there was a link to YouTube video of Chabad that showed the whole ceremony of the funeral. So he was Jewish. And I think half of our papers we did like Jewish people. So yeah, there is some kind of signal in the noise, but we won't go into that about Jewish people in science and math. Maybe we'll do a podcast about that in the future. But anyways, so what Gordon was trying to do.
Daniel, a small remark before starting. I think there's the first paper which came from the university, which is not from the United States or Europe or Russia. I think there is, I don't come across many papers from South Africa universities, so it is quite a rare thing now. I don't know what was the situation 45 years ago, but still it's quite unusual paper according to its origin, at least.
Yeah, good point. First time from South Africa and University of Witwatersrand. Never heard about it. I know the big cities in South Africa.
Yeah.
So I'll read the summary. It says the technique set out in the paper, CHAID or CHAID, I don't know, it's CHAID, is an offshoot of CHAID, automatic interaction detection. That's the previous episode we had about trees, designed for a categorized dependent variable, meaning when the outcome is categorical. Okay, and some important modifications which are relevant to standard CHAID include built-in significant testing with the consequence of using the most significant predictor rather than the most explanatory, multi-way splits in contrast to binary splits, and a new type of predictor which is especially useful in handling missing information. So in a sense, he said he takes what they did in CHAID and adds more functionality. Right now, he can handle categorical outcomes and also predictors, and also they can handle missing data or information.
By the way, Daniel, these multi-way splits are not very common today because almost all the methods, at least those I'm familiar with, are doing like random forests, like like XGBoost, like GBM. All these methods are doing binary splits.
Binary.
So it is a quite rare bird in our horizon.
Yeah, good point, Mike. So I'll read. I won't read everything. I'll read the important parts, in my opinion. So he starts by saying, I consider the problem or parsimoniously describing a large data set. So parsimonious means describing something with the least amount of words in natural language. Okay, so already he talks about some kind of dimensionality reduction. Consider many vectors, each of whose elements is a categorized variable, one of which is the dependent variable. The remaining elements are predictors, and their categories may or may not be orderable, meaning maybe there's a feature that you can order, but some you might not. A typical data set has several hundred vectors, each with many elements. Okay, so this talks about like data. Could be many samples, and each one could have a lot of features. Yeah.
There is a quite important thing which confused me in the beginning, and it appears in the second sentence. It shows that all the variables, all the predictors or independent variables are categorical as well. Not just the dependent variables, or there are no continuous variables here. Only categorical variables. The independent one, which is not very good name, but still we can call
Where
it.
do you see the sentence? Have I read
Second sentence. Consider many vectors. Each of those elements is a categorical variable, and one of each is a dependent. So the features are categorical as well. At least it looks like it.
Yeah.
So there's no continuous variables?
Yeah.
I think maybe we'll get to it because this method works also for continuous methods. I think he talks about it. You take a continuous variable or a feature and you break it into beans. So it's categorized.
I think sure. He's calling it monotonous or monotonic.
Okay, we'll get to that. Maybe he's not talking about it. Maybe I was confused.
Maybe I'm wrong, but it confused me.
Okay, so let's we'll get, if it's relevant, we'll see it in the paper.
Yeah.
So let's move on to comparison with the AID, the automatic interaction detection. The previous episode we had on the on trees. This is the Songquist paper, Morgan and Songquist from 1963. So he says here, in AID, the data are successively bisected using one or other predictor, preserving the ordered nature of the categories within a predictor where appropriate. Okay, in the AID literature, such ordinal predictors are called monotonic, while purely nominal scale predictors are called free. And he says, I shall introduce a new floating predictor that is the most useful in practice. Okay, so he says in that previous AID worked on continuous variables, and you can break them by calculating the variance and between the groups, and then trying to minimize it.
In other words,
here it's called essentially F statistic, sum of squares. Then here it says AID operates on an interval scale dependent variable and maximizes the between group sum of squares at each bisection. Again, the listeners can go back to the previous episode on AID to see how it works. Okay, the comparison, I then compares it with THAID, THAID. I won't go into that. I want to go to the algorithm that he's proposing. So again, the idea here is to handle categorical variables. Meaning, let's say the category is city that you live in, and you're trying to predict that. So I don't know, there's a list of possible cities that's not continuous. Now, how are you going to handle it? With AID, you cannot do it. Like there's no split you can do and calculate some distances. So here where his method comes in. So he says, like AID, CHAID proceeds in steps. First, the best partition for each predictor is found. Then the predictors are compared and the best one chosen. The data are subdivided according to this chosen predictor. Each of these subgroups are reanalyzed independently to produce further subdivision for analysis. So again, similar to there, although it's now categorical, we still look at some kind of feature, find a place to break, we do the break, and then we continue. So at the end, we get a tree. Still, we have a tree with splits, and depends on which feature.
And it doesn't have to be a binary tree in this case, right?
Yeah.
Categorical. Why binary?
Well, binary, yeah, it means you can be more than one split. That's what you said.
Okay.
That's what I mean.
That's exactly what you said. Yeah.
Okay.
He says the type of each predictor determines the permissible groupings of its categories, so as to build the contingency table with the highest significance level according to the chi-squared test. Okay, so because we have categories now, he's building the contingency tables. So think about it as like matrices. And then each entry, he can calculate the chi squared and then make some kind of decision. We'll get to it.
Daniel, I want to make a small remark to distinguish, to emphasize the main difference between these methods. When your dependent variable is continuous, you can build your groups, and you can compute variances of, for example, you have some category, and you build two predictors, and but your variable is continuous, so you can easily compute variance.
Yeah, you can compute distance and error.
You can compute a variance of two groups, and then you can do something which is F statistic. When you have categorical variables, the variance is more or less meaningless. If your dependent variable is nominal, the variance is meaningless because it's not nominal. Categorical, for example. Categorical, sorry. Gone with nominal, it can be a bit problematic compared to the continuous case. But if it is categorical, you have category, blue, white, and red. So how can you compute variance? So the only method you can, not the only method, but you must use some method which is adapted to categorical variables. And here, he squares, right? Not chi squares. He squares.
I thought it's chi squared. I don't know correctly.
Okay.
Yeah, in Greek it's chi, in American it's chi. So
okay. Chi squared. Okay.
Yeah.
And this is the main difference between these two papers. Instead of F statistic, they use chi or chi.
Yes.
And where you're living.
And in order to calculate the chi squared, you need to build the contingency table.
Yeah, exactly.
Meaning all the if you have a few categories, so you do like all the different combinations between them. But we'll get to that. It says chapter 2, the algorithm. Let the dependent variable have the equal or higher to two categories. Again, if there's one, there's no sense to do a lot. And a particular predictor under analysis has C that is higher than 2 or equal categories. So that's the predictor is like the feature.
Yeah, and the features are categorical. Do you remember I told you? It confused me in the beginning, but I think he's talking solely about categorical features.
Yeah, for, now, yes, I think you mentioned what happens when they are continuous. But yeah, for now, to the listeners, both the feature and the outcome, why they're both category.
Yeah.
And it says a subproblem. So now you have like features, the categorical and outcome. A subproblem in the analysis is to reduce the given C times D contingency table to the most significant J by D table by combining in an allowable manner categories of the predictor. So the idea here, if again I have some kind of a category city, because I have data and each entry has a city where it came from, could be hundreds of cities. So he says here, let's combine categories together. Some kind of reducing the dimensionality of the problem. In the case of cities, we can combine all the cities in one country to one, but that's just a heuristic. He proposes an algorithm that will do this combination. He says, conceptually, we may first calculate statistics, Tj I in parentheses, and then the usual chi-squared statistics for the ith method of forming the J times D table. Again, just without confusing with all the mathematical jargon, the idea here is given a contingency table, you can calculate the chi-squared. And then per each entry in the contingency table, and then you can take the maximal one. It says here, then if Tj star is the max of all the possible calculation, and so this chi-square statistic is the best for this specific table. And then you can do some significant tests. Okay, so again, the idea here, let's say we start with some categories for the features and the outcome is also categorical. You build a contingency table, which is like a matrix with all the possible combinations between the categories. For each one, you calculate the number of, like, I would call it overlaps, or there is a mathematical definition.
Similarities.
And then you, yeah, how would I call it, Neil?
I understand it's the similarities.
Okay.
Like merging similar rows in the table. And the similarity is using this test that he describes here.
And then you calculate the chi-squared of the whole contingency table, and then if it's higher than some kind of number, it means that it's not random. Yes. That means there's some kind of significance or signal in it. And then he continues. In the case of a monotonic predictor or a dichotomous tree predictor, the Tj, I don't know how I call it.
Star. T sub j superstar.
Star, yeah, star may be found by the procedure of Fisher. Okay, yes. And again we have Fisher, but not a paper we went over, but still.
Yeah, he quotes a paper here.
Yeah, Fisher, and he says this dynamic programming procedure is computationally of order of C squared. So we had a paper about dynamic programming by, I think it was Bellman. And dynamic programming is when you have some kind of a problem that you can break into some problems, solve the sub-problems, and use the results of the sub-problem to solve the original one. So it's like a recursive algorithm. Again, listeners could go listen to that episode. He coined the term the curse of dimensionality in that paper, which is cool. And so he said, you can solve the problem by doing dynamic programming. What do you mean here, dynamic programming? So if I have a feature with some categories, as I said, again, cities, and I want to combine them. So in theory, I should run all the combinations of all possible, how I can combine two cities together into a new category. Now I have a new contingency table, calculate the chi-squared, see if it's significant. If not, do it again. So this idea is super computationally expensive.
Yeah.
Takes a lot of time.
Not just two cities, any subset of cities, because 2 in the power of c is all the.
Yeah, you can combine 3. That's right. You can combine 2, you can combine 3. Every combination, combinatorically, it's exploding really fast.
Yeah.
And he says when d is higher than 3, a free predictor cannot have its categories ordered in general, and the Fisher's method cannot be applied. Instead, the standard application of dynamic programming to permutation type problems can be applied. And now it is exponential. It's 2 to the power of c. And he says, while dynamic programming is feasible on a computer for a single predictor at a single stage of the analysis, it would be unrealistic in a practical example where there are many predictors, and the analysis extends over a number of stages. I therefore propose an alternative method, which although it does not guarantee that the optimum solution will be found, has yielded very satisfactory results in practice. In contrast to dynamic programming, the computational effort is in of order C for monotonic predictors and on the order of C squared for free predictors. So now we have polynomial, thank you very much, time instead of exponential, if we use his method. So he says, again, you can run all the possible combinations with dynamic programming and maybe help you reduce a little bit the search, but it's too expensive. I have some idea that is not optimal, but close enough. I think that's what's his motivation. And then he writes his algorithm. So step 1, for each predictor in turn, so for each feature, cross-tabulate the categories of the predictor with the categories of the dependent variables and do the following. So now we have like a for loop that goes over each feature and writes down all the categories that the feature has and all the categories that the outcome have. Then, okay, inside the for loop, it says find the pair of categories. It's step 2 of the predictor, whose 2 times d subtable is least significantly different. If this significant does not reach a critical value, merge the 2 categories. Consider this measure as a single compound category and repeat the step. So now he trying to combine categories. As I said, if we're looking at cities, trying to combine cities together, he combines 2 cities. Again, so the combination is binary, so it's just 2. See if it affects the significant testing. If it doesn't affect, perfect. It means that we can keep this merge of 2 categories together. So what's his motivation? He's trying to reduce dimensionality, right? He's trying to combine categories together to the, let's say, the minimal amount of categories you can have per feature that doesn't affect, let's call it, the significance, or it's like the error in our case.
So basically he's trying to cluster features or feature values which has similar outcomes or similar dependent variables.
Then he says step 3. So we're still, after we did this merge of categories, for each compound category, so this is like the new category after merging. Let's say we have San Francisco and Los Angeles, so it's Los Francisco category. And now he says this new category, which consists of 3 or more of the original category. So now let's say we've merged 3 or more cities. He says find the most significant binary split. into which the merger may be resolved. If the significance is beyond a critical value, implement the split and return to step 2. So here it says I combine at least 3 categories together. Let's see if I can break them.
Yeah.
Okay, so the idea here, if I'm thinking about maybe some kind of reducing overfitting, or like if we're talking about trees, like pruning, that's what I'm thinking about, because maybe I combined by chance too many categories together. Let's see if I can break them a little bit.
Unmerge.
Yeah, which is unmerge again.
Yeah.
Also, you can look at it as exploration, exploitation. The beginning is very greedy, he's combining, and then he says, okay, maybe I should step back and break it.
Let's see if we can break it in the... Okay.
Then step 4. So that's now he did all the combining of categories.
Decombining.
Yeah, decombining into compound categories. That's how we call them. And then calculate the significance of each optimally merged predictor and isolate the most significant one. If the significance is greater than a criterion value, subdivide the data according to the merged categories of the chosen predictor. So this is like the classical split that we covered in the previous paper.
But only if it surpasses some threshold, right?
Yeah.
It wasn't
because
like
we're still doing a chi-squared testing.
Yeah, I know, but this threshold, I think that in the paper that we reviewed, we just took the best one, and then we
That's
split.
right, and split.
Here, he's not only taking the best one; he's first checking that the best one is high enough.
That's a good point. Yeah. That's right. It's also some kind of regularization or something like that.
Yes, it's regularization for sure. Yeah.
By the way, for more than tree-based techniques, we are doing it in only one direction. We are only splitting, and we can't come we can't come back. We can't decide not to split, but we don't merge. You know, in random forest or in all this XGBoost and methods like this, we decide when to split. We have some regularizations. You know, we are computing the entropy decrease and stuff like that. But the only decision that we can take is not to split. So we are not merging. So if we already decided to build some tree, maybe there are some methods that you can discard the whole tree. But yeah, I think in the XGBoost they are doing something like that. But
they're doing something, yes.
Yeah. But here it is interesting combinations of merging and splitting. So you are splitting and merging at the same time. And you know, it is interesting because it relies on chi-square. Okay, today we are doing it with entropy decrease. I don't remember what is the name, or some variance decrease. Gini, and here he is doing it with the chi-square, and it is interesting because it is different from how we are used to see now.
Yeah, and the last step. Sorry, Nir. Yeah, and then I'll say the last step.
I 100% agree. I don't think the current trees, they don't do this merging and demerging that he's doing at all. They maybe do pruning, they maybe do bagging, right? Ensemble stuff, but they don't do they don't merge rows like feature vectors or rows into a what you call the compound category, and thus basically it's, for me, it's kind of like exactly what Daniel said. It's dimensionality reduction.
Yeah, but only thing that which is done, at least for XGBoost, is you can discard the whole tree, so you don't merge, but then you do some splitting, and you can decide just to cancel it, or not to use it. Maybe it's some kind of, you know, some implicit merge.
Yes, like pruning. You can also limit the depth. You can, and so on. But it's not like this. It's different.
Yes, exactly.
That's what I'm saying. Yeah.
Cool. So step number 5, last one. For each partition of the data that has not yet been analyzed, return to step 1. This step may be modified by excluding from further analysis partitions with a small number of observations. So yeah, his method works when you have enough observations. Otherwise, the chi-statistics won't work, won't pass significant testing. Okay, here he talks about some kind of asymptotic guarantees regarding this method. I won't go into it. Then chapter 3 is significance of the predictors. So here also he talks about some kind of correction that needs to be done. The Bonferroni.
Yeah.
Again, I don't want to read everything here. If you can tell a few words about... Yeah, tell me.
Yeah, I think it's another way of regularizing this process. The problem is that this greedy type of merging can cause problems. That you're not overfitting, basically. That you're not aware of this problem when you do it. It's like, think of it like observing. Well, if you toss a coin, right, and you do it once, there is 50% chance that you get heads, for example. But if I now toss the coin 20 times, it's very likely that I will see heads at least once. So it's kind of like that. It limits the luck, so to speak, that this kind of process can introduce.
Exactly. By the way, it is quite standard procedure. I'm trying to recover from my old memory. I think I studied this stuff maybe 25 years ago. When you are computing many p-values and you decide that your target p-value is 5%, and you are making decision for all p-values which are less than 5% or 0.05, but you are doing it a lot, then it increases the probability that you do some wrong decision, because you are doing just exactly what Nir described, and I think the correction which is done when you compute many p-values and making decision, that is also called Bonferroni.
That's right.
The computation is a bit different, but I'm not sure about it. Maybe it's quite similar computation.
Yeah, so here instead of p-value, it's the chi-squared that you calculate a lot of times, but you're totally correct, Mike. Because we have many calculations, many by luck, we'll get something right. And also, as we make more, we increase the chance that will be significant. So that's this correction, and it gives for each type of feature, if it's monotonic or free predictor, the different correction. So that's chapter 3. Chapter 4, empirical investigation. Also, I won't go too in depth here, but he gives an analysis he has done on some data that he describes. And as Nir mentioned, you a priori choose the error rate that you can accept. So here it shows 5%. He says, in each case, the merging criteria was significance at the 5% level.
So it is p-value on the chi-square test.
Yeah.
Okay.
And he gets it, and the results. There's another example. And here he runs on, there are monotonic predictors, free predictors, and 26 floating predictors.
By the way, floating predictors, I'm not sure I completely nailed it down. Floating predictors are missing values. What are these?
Actually, I think it's missing values.
Okay.
Then because here a free predictor is something that could be whatever, as far as I understand.
Like orange, apple.
Here, this is a floating predictor. It says articulation mathematics symbol. So I think it could be...
and it's labeled question mark for students who did not take mathematics.
Yeah, so when you have like a missing data
it's missing.
Yeah. By the way, I asked
Got
3 LLMs, and then all 3 of them told me that it is missing value.
When? Right now?
No, not right now.
Oh, okay.
Yesterday, I asked
Okay.
Gemini, ChatGPT, and Claude,
Nice.
and got a
Question.
very very similar answer.
Okay, it makes sense. How
By
do
the
we...
way, let's take a look at the size of each data set. You have several hundreds of points, and you have 40 features, and these were the data sets of 80s. You know, we got used now for data sets of trillions or dozens of trillions of tokens, or millions or tens of millions of rows of tables in your databases. But here, only 45 years ago, this was a quite classic, typical data set, 900 points. And try to do something with 900 points.
Yeah, it's...
and here is the tree, There is a single tree in this paper, and now we are looking at it.
Yeah, but it's not a binary tree. That's what's nice
not
about
a binary. Yeah, exactly.
Yeah, exactly. That's the apparent observation. So I started with 669 observation. Then he breaks, the split is on the feature number of commercial subjects. And you can, well, again, to the listeners, he did one merge. So category 3 and 4 are merged together. And there's the 2, 1, and 0. And then there's like binary splits type of afterwards in the tree, which is super interesting. So yeah, that's the end. And let's see. I want to see the feature paper.
Daniel, let's take a look at the acknowledgement. Part of this work was done while the paper was on a long leave at Bar-Ilan University.
Yeah.
I missed it when I read this paper.
Yeah, me too. I haven't read it. Interesting.
So this paper
to the listener,
was research in Israel.
Yeah. So we have some connection to non-binary trees.
Yeah, and it was research in Israel. So to the listeners who have a problem with Israel, this is not a paper for you.
They can write a paper about gender fluid trees and not binary trees. And get accepted to many let's say
that's
impactful journals.
Missing values.
Now it can be quite problematic, in 2025 it can be a bit problematic, all this gender fluid. A year ago it was cool, but now it is let's say a bit less cool.
This paper from the 60s, they don't know how to handle this kind of data, fluid data.
Yeah.
No, it's not the floating.
It is. I'm kidding. He predicted the future.
Okay, cool. So that was a nice paper.
And the Fisher paper here is on grouping for maximum homogeneity. That's a paper for 1958. Maybe we should survey this paper as well.
Yeah. It looks a good paper.
It does look like a good paper for sure.
Sure. I'll look into that.
Yeah, by the way, the second paper on the list of average analysis of contingency tables. I'm not sure it is a paper. Maybe it is a book.
Maybe it's a book.
Yeah, it looks like a book.
Okay.
And what is the first one? Alchemy in the Behavioral Sciences of Einhorn.
Yeah, interesting.
No idea.
Maybe we should do this paper as well for you, Daniel.
I think it might be opinion. What's like public opinion
quarterly?
Yeah, but what's the opinion? We'll see. I'll look into that as well.
Okay.
But I do plan in the future to go over more papers that at the end will get us to random forests and XGBoost, etc. So we'll get there as well. And soon we can get to SVM and stuff like that, probably.
SVM
Yes.
is right. It is of.
It's already 90s. We're not there. We're almost in the 80s. Yeah.
Okay.
Well, we're not going back to 58 for Fisher, so
No, we might go back. We might go
yeah, we
back.
might.
We
Yeah.
we have
It's
a place for Fisher always. So
exactly. Fisher has a special place in this podcast.
yeah, and he has a place
Yeah.
in our heart. Yeah.
Yes,
So we are not
he does.
monotonical. We are not going to be monotonical.
No, no.
Chronologically sorted. Our episodes are not
And-
chronologically sorted. You can
not
sort
chron-
it after it, but we record it. But we are going to record it not in the chronological order.
Yes.
Perfect. So thank you very much, Mike and Nir. I hope the time was okay with you. Yeah.
It's 11:20 in the PM here, so
Yeah,
it's
so
never better. Everything is quiet.
Yeah.
yeah.
Cool.
So time to do a workout, Nir.
Yeah.
Yeah, I already did my workouts for today. So
Oh yeah.
I'm going to do it.
Amen, brother. Yeah. So thank you guys, and I'll see everyone next week.
all right, see you guys. Bye.
Bye.